Hello, my name is Alvaro and I am a PhD student at the University of Colorado Boulder. In this paper, we study the uncertainty in the electron beam dynamics in the context of active spacecraft charging applications. As many of you know, in the last couple of years, our laboratory has explored different applications to the spacecraft charging phenomenon, like for instance, using electron beams to induce an electrostatic potential difference between two spacecraft in geo-orbit and measuring the potential of the second, or using that potential difference to induce a net force over the target as a way to remove space debris or induce significant effects in our target. All these applications share something in common, which is that they employ electron beams. But the questions arise on whether how accurately can we direct our electron beam towards the target. What is the uncertainty in the landing properties of such electron beam, and which model should we use? So let's start with the third question. After a short bibliography research, you will notice that there are many different electron beam models with different characteristics. However, the most popular of them, like console multiphysics implementations of CMIUM, are particularly computationally expensive. And we didn't want such a computationally expensive model. We wanted to develop something which was easy to implement, computationally efficient, and also physically reliable. So we came back to a very old assumption used in many works, which is the infinite cylindrical beam model. In this context, we also decouple the expansion and the deflection phenomena in such a way that the expansion of our beam is only due to internal fields and is completely determined by them, and the deflection is only due to external fields. In the first case, we compute internal electromagnetic force by means of a simplified cylindrical beam model, and we impose an initial divergence angle given by this delta parameter to our beam. For the deflection, we assume the multispheres model that gives us an accurate but computationally fast representation of the electric fields around our spacecraft. In this way, we uncouple both phenomena and give rise to a computationally efficient framework of analysis that is actually enhanced due to a non-dimensionalization of the problem. We are assuming that the beam experiences small deflection angles, that the expansion angles are also small, and that the beam cross-section is asymmetric. So first of all, the question is, okay, how good is this model? In order to assess that, we define two validity metrics. The first one is the total deflection angle of our beam, and the second one is the normalized gyro radius. What the first must be small, the second must be large, and you will see very, very soon why. So in order to explore this experimentally, we built this setup where we direct an electron beam towards a phosphorus screen, and this direct electron beam is deformed and deflected by means of a spacecraft-like electrode. The shape of the beam is observed with the phosphorus screen and measured with a Faraday cap that are moved thanks to this linear state here. We build a representation of this setup using the multispheres model. And here you can see a case of analysis where the beam is deflected and expanded at the same time. So, first result, if we change the electrode potential from 0 to minus 500 volts, we observe how the beam, first of all, of course, is deflected, but also how the cross-section is deformed. It's elongated because it is being focused towards the phosphorus screen. From our numerical results, we observe that the normalized gyro radius, that is represented as a function of the electron beam position or the propagation position, goes down. That is, the gyro radius decreases logically because the electric field is stronger, from about 10 to below 2 in the normalized scale. We also observe how the deflection goes from 3 degrees to 16 degrees. And it turns out that still for the 300, more or less the 200 volts case, the electron beam cross-section has not been deformed significantly, and that corresponds to the 3 normalized gyro radius case and the 6 degrees deflection. If we, instead of change the potential that we here set to minus 100 volts, change the electrode heating, we observe a very similar effect, but in this case, the deformation of the beam is not as significant. And this deflection, in any case, is due to this second minimum in the normalized gyro radius. As you can see, is much larger than in the previous case, and that explains why the electron beam is not, the cross section is not deformed as much. Also, the total deflection angles remain reasonably small. So, okay, we have observed which is the validity range of our model, and we define this for the uncertainty quantification analysis. We define this base scenario where we have two spacecraft with different potentials and an electron beam at 5 kiloelectron volts directed from one of them to the other. That is at minus 2.5 kilovolts. If we represent the validity metrics for the base scenario of analysis, which is the red case, you will see how the electrode, the normalized gyro radius remains always above 5. So the model that we have just presented should be valid for this case, because also the deflection is about 5 degrees. We also represent the final, the beam radius evolution as a function of the initial deflection. And there is not something interesting to note, which is that when such angle is 0, that is, we have a perfectly collimated beam, there is a repulsion due to the electrostatic interaction. And this repulsion overcomes everything else, every other effect. But when the deflection angle is slightly larger, 0.2 degrees, we see a quasi-linear evolution, which means that we have actually two regimes here, a repulsive regime and an inertial regime. So actually one idea for the future would be extending the validity range of our model by switching between this repulsive regime and this inertial regime. So in our uncertainty quantification analysis, we define 702 parameters. This is a high dimensional problem. And so the only feasible analysis is Monte Carlo. But since the model is extremely efficient from the computational perspective, only taking 0.6 seconds to compute, we can take many realizations and we don't need other techniques such as multi-level Monte Carlo analysis. If we implement in this model a reasonable set of parameters and a reasonable set of distributions, all of them are normal distributions unless the initial divergence angle, which is an uniform distribution. And in order to determine which one of these input parameters affects most these outputs, we run a sensitivity analysis with a reduced set of 14 parameters. So what we get from the high-dimensional Monte Carlo simulation are these probability distribution functions that are extensively described in the paper. It is interesting to note that for these inputs, we hit the target solar panel in 93.9% of cases, but we don't do it with very high accuracy because of the large spread in the electron beam centroid. Reaching just a 0.3% probability of hitting a 20 centimeters diameter target around the target in the spacecraft. As you can see here, the centroid spread dominates over the radius spread, and we get from the model also the time of flight, which is useful for several applications, and the final electron beam, which has a particular incidence in the secondary electron yield. Also, it is interesting to note that the initial divergence angle, which was modeled as an uniform distribution, has a large influence in the final radius of the beam. If we run a fast global sensitivity analysis and we represent the sensitivity or Sobol indices, which basically tells you which percentage of the variance is due to which input parameter, here these are multiplied by 10, you can see that the different outputs of the system are depending on just a few inputs. Like for instance, the final radius is mainly dependent on the initial divergence angle, logically. We also observe that this reduced model has almost the same variances in the outputs as the full model, and so the reduction, the dimensional reduction, is appropriate for this case. So conclusions: the short-term propagation of electron beams is a very specific problem and can be addressed, or at least under certain validity ranges, with a quasi-analytical model that is computationally efficient and accurate. The validity range may be extended by means of a switching model, as I previously described, and the most influential inputs of this problem can be determined for a particular case of analysis using a fast global sensitivity analysis. So thank you very much for your attention. If you have any questions, please feel free to reach out at any of these links. Thank you.